Welcome everybody to this week's edition of the joint Heidelberg Astronomical Colloquium. It is a great pleasure to welcome John Kirk, one of our own in Heidelberg for many, many years, who will talk to us about pulsar winds, about high energy astrophysics in these extremely interesting and compact objects. Before we go to the talk, let me say a few words and introduce the speaker to you. John has studied in Oxford. He finished there with his PhD, then went to Göteborg for a year to work on plasma physics. From that, he moved to the continent, to Garching at the MPA, and he stayed there on and off. He had a 1-year stay in Boulder, Colorado, and a 1-year stay in Sydney until 1990. And in the same year, he moved here to Heidelberg. Hello, welcome. Beautiful hats. And he has stayed here ever since as a group leader and staff scientist at the Max Planck Institute for Nuclear Physics. And I should mention, now he actually has time for research because he is in pension since February this year. So we are very welcome that he finds the time to give this talk to us. So, welcome, John.
Thank you for the... So, is the microphone working, is the first question? Yes. Thank you for the kind introduction. As you point out, I now have lots and lots of time on my hands to do whatever I want, and at the moment it seems to be mostly research, I must say. I'm going to try and give you at least an overview of pulsar winds and why they're so interesting. And I should mention at the beginning the people with whom I've worked on this subject in the last few years. At the moment, I'm working with Gwenel Jacinti, who's a postdoc at the MPIK. And then there were 3 students who've completed PhDs on this topic, also at the MPIK and here at the university. Simone Jacquet, Ivona Mochol, and Joanna Arca. And thank you to those members of the audience who took part in thesis committees, if there are any of them here. Yes. An important piece of work which I'll mention was done together with Takanobu Amano, who's now in Tokyo. And at the moment I have collaborations with Yuri Lubarsky, Keshet, and Daniel Kagan at Ben Gurion University in Beersheba, and that's funded by a German-Israeli Foundation grant, which is at least one reason why I'm only partially in retirement. Okay, so what about these objects? Most of you will know all of these details in the first few slides, but we have about 2,000 pulsars. Most of them, within 2 or 3 exceptions, are in our galaxy. They emit pulsed radio emission, almost all of them. They also emit pulsed optical and gamma, some of them do that. They are collapsed stars, neutron stars, strongly magnetized and rotating with a period of somewhere between 1 millisecond and 6 or 7 seconds. Okay, but about, say, 50 or perhaps a little more of them are surrounded by diffuse emission. Diffuse emission in the radio, in the optical, and in this case, in the X-rays. Most of these pulsars surrounded by diffuse emission are not the oldest ones of these 2,000, but the middle-aged ones. They're several tens of thousands of years old. I should say that all of these pulsars are slowing down. They're measured, their rotation period is increasing, and so therefore they're losing rotational energy. And this presumably is what's powering the diffuse emission around them. Some of them, however, are young pulsars, powerful ones, which are only a couple of thousand years old, and this is one of them. And they have really quite remarkable nebulae surrounding them. So this is a Chandra X-ray picture of one of the powerful ones, 1509. And you can see that now, since several years actually, one can resolve these objects also in TeV gamma rays. In fact, pulsar wind nebulae turn out to be the dominant source in the galaxy for galactic source catalogue in TeVs, as you can see in this recent publication. And this kind of observational advance, mainly because we now have very good high-resolution images at high energy, has stimulated a lot of theoretical work. So this was the same object as you saw previously, but of course the most famous object and every theorist's favorite is the Crab Nebula. Here is an optical and X-ray picture of the Crab Nebula, and this is the object to which I'll be referring mostly because, first of all, it's the most powerful one. It has a competitor in the LMC, which is about the same power, but it's certainly the most powerful pulsar which we know in our galaxy. And the pictures, which you can see here, just have a resolution which is not much better than the others. So here is a little bit of public relations work now, just to motivate the theoretical part of the talk. You can actually take a movie of this object. And on the left you see X-ray, on the right optical, HST and Chandra. This is the pulsar down here. And you can see that there are rings of emission surrounding the pulsar. And you can also see that there is a gap between the central object and the beginning of the diffuse emission. This is actually a superposition of 7 images taken at intervals of about 1 month, so it's about half a year in the life of the Crab Nebula, and it's looped something like 20 times during this little video. So we're going through maybe 10 years of the Crab pulsar and its nebula. And you can see there's lots going on, and clearly stuff is coming out. Doesn't seem to be falling in. And indeed, that's the subject of the talk. So what I'm interested in really is the gap between the pulsar itself and the nebula. Ah, good. Okay, so much for the general introduction. That's why these objects should be interesting to you. The rotational energy, by the way, in the neutron star of the Crab pulsar is still about 10% of the entire supernova energy. So there's quite a bit of energy available to power this diffuse emission. You've had the introduction. Then move in a moment to putting this in more historical context. And then there are 3 bits of physics about the pulsar wind. That's the connection between that central object and where we see the emission that I want to describe. And these go under the headings of the striped wind, then the termination shock, and finally my current favorite topic is gamma ray flares. So with the increased observational capability, much of the theoretical work went into modeling the morphology of that nebula. And there are now quite refined 3D MHD models which will show you what the structure of the nebula is if you inject accelerated electrons at a certain point with a certain spectrum. And to me, that's fine. It confirms that MHD picture of the nebula is okay, but it doesn't answer the question of how the rotational energy gets into the energized particles. In other words, how the wind transports the energy outwards. Well, Crab is a very famous object, possibly the most intensively studied object outside of the solar system. And it was in 1954 that Shklovsky showed that the diffuse optical emission, the Crab Nebula was well known, the diffuse optical emission must be synchrotron radiation. That is the radiation of relativistic electrons moving in a magnetic field. So it's clear that the magnetic field had to come from somewhere. And indeed, back in '57, Australian scientist Piddington demonstrated that this magnetic field couldn't just have been lying around, but simply because the ionized ejector from the supernova would take out the magnetic field with it. So it has to come from the central star itself, and it's a fairly strong magnetic field too. Well, of course, people were wondering what kind of star it could be and how this might energize the nebula, and Franco Pacini, in a prescient paper in '67, this, by the way, was before the discovery of pulsars, suggested that, in fact, there must be a neutron star at the center of the nebula, a very strongly magnetized neutron star, and rapidly rotating, and that the dipole radiation from this oscillating magnetic dipole would be absorbed in the surroundings at some point, and then radiate. So this was quite remarkable because, as I say, rotating magnetized neutron stars were not known to exist at that point. They were discovered about a year later. And it took about another 12 months before the Crab pulsar itself was discovered. It was one of the very first pulsars to be seen. And interestingly, it was not discovered as a directly pulsing source. It was discovered as an intermittent radio source. In fact, the Crab emits what are called giant radio pulses, which occur not exactly at this rotation frequency of the pulsar, but somewhere within a rotationally modulated envelope. And there are also weaker radio signals which come more or less regularly. So that was the discovery of the Crab pulsar. But this means we need to get magnetic field out, we need to get particles out, relativistic particles, and getting those from a neutron star is not so easy. In a usual stellar wind, you would heat the corona until it becomes hot enough to escape, it would boil off the star, and then you would have some mechanism for accelerating the MHD flow through a sonic point. But these winds have to be different, because the potential energy of the neutron star is so deep that you cannot lift protons off the surface and eject them. This would require much too much energy. In fact, it's difficult to get any matter out at all. You can only really do it using electromagnetic forces. And so by counting the number of radiating particles, you can estimate this from the nebula, and by looking at the power in the wind, you can define this dimensionless parameter, which I think Kurt Meitel, one of the early pulsar physicists, used, and this is extremely large. It's typically 10 to the 4 or 10 to the 6. This doesn't tell you, this large parameter, whether the energy is in particles or in magnetic field. There's another one which I'll introduce in a moment, which tells you how that is distributed. It just says that if by any chance you manage to put all of this into particles, then this will be the Lorentz factor of each particle. Okay, so we clearly have here an extremely light wind. The energy is not in rest mass. It's either in very relativistic particles or fields. And the ways to try and get hold of this theoretically went along two lines. First of all, people tried to generalize what Pacini had suggested, that it's an oscillating dipole and therefore something like a vacuum wave which is propagating outwards and at some point gets absorbed. So if you do that, then there's another very large parameter which crops up immediately, and that's the ratio of the gyro radius of a non-relativistic particle in the field, let's say at a one wavelength from the star. That's a very high frequency because the field is strong, compared to the frequency of rotation of the star itself, which is quite a low frequency. And this number is something like 10 to the 11 at what's called the light cylinder radius. It's the wavelength over 2 pi radius for the Crab, and it's extremely large for all known pulsars. That is a bit of a problem theoretically. It means that if you put a test particle into this wave, it will achieve extremely relativistic energies within a fraction of an oscillation of the wave. So it will also move quite a long way within a fraction of oscillation of the wave. So you cannot treat the interaction between the particle and the wave as, you cannot linearize it like you would do in Thomson scattering, for example, and assume that the particle is almost stationary and just oscillates a bit. These waves have an extremely powerful effect on any test electron or positron which is put into them. So that was at the distance from the star, which is wavelength over 2 pi. As you go further away from the star, the wave gets weaker, of course. It's spherical, more or less. And at the point where the nebula starts to glow, which we can measure actually quite accurately now, it's at about 10 to the 9 of these radii. The strength parameter, as I'll call it, has dropped to a few hundred. So this means if you put in a particle somewhere near the star, you might get a Lorentz factor of 10 to the 11, neglecting losses. If you were to put in particles at rest near the termination shock, you would get a few hundred. So it's crucial how you get particles into this wave. And that was also shown by Oestreicher and Gunn, who did the first calculations of test particles in such waves. To quote from their paper, if they got the right injection phase and the right injection position, they could get protons, in this case, with energy up to 21 eV, which has been exciting cosmic ray physicists ever since. And there are now indeed people actively working on models in which very, very young, powerful pulsars are responsible for producing ultra-high energy cosmic rays in this way. But that's not the subject of this talk. This kind of work progressed. This was test particle work by Oestreicher and Gunn, but if you have enough particles, then when they start to move, they create a current, and the current acts back on the wave. The upshot is that this is a collective process, and it's a nonlinear wave. And so if you really like plasma physics of strong waves, you can look at these old papers. And what the upshot is that within a certain radius, these waves cannot propagate. There are just too many particles around. You know that an electromagnetic wave is reflected by metal because its frequency is below the plasma frequency of the metal. It's the same thing here with a relativistic correction. Close to the star, the density is just too high. The plasma frequency is too high to allow these waves to propagate. So they fell a little bit into disfavor. And so it's about 10,000 or 1 million light cylinder radii where you can first have these waves propagating, which incidentally is still well inside the termination shock where the nebula happens, so there could be some spontaneous conversion at some stage. It's not really clear whether that happens or not. So these became a little bit unpopular because people were happy to ditch all the plasma physics with the reasoning that, okay, well, they're not launched anyway. So, and the second approach, which is technically perhaps a little bit easier, is to try and forget about the waves altogether. Assume that maybe they're not launched, or maybe they're damped very quickly. And it was Kennel and Coroniti in a couple of papers produced the first model which was able to explain at least the spectrum of the Crab Nebula in this case, from optical to X-ray. It didn't explain the radio spectrum, but this was the first of those MHD models I mentioned in the introduction, which assumes that you have some accelerated electrons injected somewhere, and you see what kind of emission they produce. What could have accelerated them? Well, one possibility is that the termination shock itself, we think that the shocks associated with supernova remnants are successful accelerators of cosmic rays, so why not this termination shock? Why can't it accelerate electrons, or at least the electrons and positrons, which we expect to be in the wind? It's possible. It's a very relativistic shock. And if you look at the theory of relativistic shocks, first order Fermi process, you find that the spectral index is actually not too bad. It's fairly close. But there's a problem with this explanation. And that is that the magnetic field gets out from the star because it's being wound up into a spiral. So by the time you've gone 10 to the 9 light cylinder radii out, the fields are all toroidal. And therefore, if you have a radial wind going in a toroidal field, the shock front is going to be perpendicular. What makes the acceleration in this first order Fermi process is repeated crossings of the shock front in which particles diffuse. But if the magnetic field is in the plane of the shock, and that's what a perpendicular shock is, then the magnetic field stops the particles from moving from one side to the other. As soon as they get downstream, they tend to be dragged away. So this is a theoretical problem which inhibits the simple explanation presented there. Here, then, is the spectrum which we really want to one day understand. This is the synchrotron spectrum integrated over the entire Crab Nebula, from radio up to TeV gamma rays and even PeV higher. And I want you to look at the moment just at the black points, which are the nebular spectrum, the steady nebular spectrum. We'll come back to the other points a bit later in the talk. There are two regions which are crying out for a theoretical explanation. And the first one is this radio spectrum, which has flux about nu to the minus 0.3, which is very hard for cosmic sources, implying a particle distribution of gamma by minus 1.6. I should say at the moment I have no explanation for this particular part of the spectrum. There are various competing models, mostly involving reconnection, but at the moment none of them is really convincing. The other part, and that's the X-ray part I just mentioned, is here. And we see there's a very nice couple of decades with a power law index of about 2.1, which means dm by d gamma in the electrons and positrons of about 2.3. And that was indeed the spectrum predicted by the ultra-relativistic shock theory. Well, I do have a theory for this one, and I'll get to it after talking a little bit about the striped wind. Okay, so we have magnetic field and waves and particles, all to be dealt with at the same time. And the first more or less consistent approach to this was one by Coroniti, who suggested, since he was a solar physicist or worked on solar physics, that it's rather like the solar wind, where you have an equatorial current sheet, and this is because the pulsar here rotates and wraps the field up, but it wraps alternate polarities, one from the north and one from the south, into a pattern which looks like concentric stripes. In between these stripes you have magnetic field in opposite directions moving out. And this is observed in the solar wind too. What he then estimated was reconnection, because he knows that if you put magnetic fields of opposite direction together, they can dissipate and heat the plasma in between, and therefore put the energy from the magnetic field into the particles. And he was happy to find the result that within a few light cylinder radii, these stripes would just go away. That means that this parameter sigma, which I perhaps should explain first here, which started off large, became small. Now, sigma tells you the balance between particles and magnetic field. It's the ratio of the pointing flux carried by the wind to the kinetic energy carried by the wind. So it's this large dimensionless parameter, which is just the luminosity, divided by the Lorentz factor of the outflow. And this is thought to be also quite large at launch. But out in the nebula, it has to have gone down to something well below 1, which was and is a little bit of a problem. This was Coroniti's solution, reconnection between here and here of just a few wavelengths. There's another parameter at the bottom here for the aficionados, and that is how many electrons do I have? It's not just the balance between the magnetic flux, so the Poynting flux, and the kinetic energy, which is important, but it's the actual number of particles which are in the flow. And that you can get from these other two parameters. Remember, that was the strength parameter of the wave, and this is the luminosity. So this is quite large. It tells you how effective the star has to be at making pairs in its magnetosphere, which are then going to flow out. Well, it was also Kirk who suggested this picture, that the fields arrange themselves in this pattern and it then reconnects. But the trouble with that is the following. In a radial relativistic wind, there are two competing forces. There's, first of all, the pressure gradient outwards. The magnetic field goes down as 1 over r, so the magnetic pressure is decreasing outwards. You would expect that to accelerate the wind. But there's also magnetic tension, because the magnetic field lines are toroidal. They hold back the flow. And if you look at the equations, you find that these two effects cancel exactly. And so a relativistic wind actually would like to have a constant Lorentz factor and a constant magnetization as it goes out. If you now separate regions of magnetic field by hot plasma, as Coroniti is suggesting in these current sheets, that changes, because in the hot plasma you have pressure equilibrium between the plasma and the magnetic field, but you don't have the magnetic tension anymore. And so, because the tension is going away, the whole wind starts to accelerate outwards. Now, you might think that's a small effect, but in these winds in which there are so few particles and so little inertia, it's quite dramatic. You get acceleration with Lorentz factors proportional to some power of the radius. And exactly what power that is depends on what kind of assumptions you make about how quickly the magnetic field heats the plasma. There are various physically motivated assumptions. There's a minimum rate and there's a maximum rate, and you can put one in between if you want. But the upshot is that reconnection in these stripes does not appear on theoretical grounds to go very quickly. It leads to relatively slow dissipation and bulk acceleration. And part of the slowness of that dissipation is because there's a Lorentz dilation of the timescales involved here. If I'm getting Lorentz factors up to 10 to the 4, 10 to the 6, then it looks as though microscopic processes in that current sheet are going extremely slowly when seen from outside. So slow means now that the reconnection would in fact not happen before you get to the nebula, before you get to the termination shock. However, there's a caveat. All these models are based on a particular physical picture in which you have a plasma in thermodynamic equilibrium with a certain equation of state separating the two opposite magnetic fields. And that's inconsistent at some point, because when you get far enough out, the magnetic field gets so weak that you can't keep the plasma in these sheets anymore. And so if it were trying to be isotropic, the radially propagated particles would escape. To get around that problem, you can make a different model of what is separating these two oppositely directed bits of magnetic field. And to do that, you just need to replace the hot current sheet by a region in which the magnetic field slowly, or rather rapidly, changes direction from one polarity to the other. And it can do that without having any hot plasma to keep pressure equilibrium going. All you need to do is arrange that there is a current parallel to B, and it will create this kind of magnetic shear. So it's possible to build a self-consistent, if you like, force-free structure, a magnetic shear, which separates these pulses, these oppositely directed regions. And if you do that, you get a slightly different answer. It's not now the fact that the magnetic field has gone away, so there's no tension, so the thing accelerates outwards. What happens now is that when the inertia of the particles becomes important, and you'll see where in a minute, there arises a slight misalignment of J and B. And this J cross B force then causes, again, the whole wind to accelerate outwards. So the picture you have there, and this was some work with Ivona Mochol, sorry. And what I've plotted is the radius. This is in units of light cylinder radius, of course. So we're already at 1,000 here. And the Lorentz factor, or alternatively this magnetization parameter sigma. You see with this picture there are 3 phases to the wind. The first one is MHD, no change in Lorentz factor, nothing happening. The currents which are required to keep these magnetic fields in place are so small that the particles can easily provide them, even though there aren't many particles. So the particles carrying the current are actually drifting rather slowly. But at a well-defined point, this stops and the inertia of the particle becomes noticeable to the plasma. And then we have a gamma proportional to R now, and sigma correspondingly proportional to 1 over R. What seems to happen from these solutions, and the solutions to the nonlinear evolution of the wave, analytic solutions, is that those 2 boundaries between the opposite regions of magnetic field move together and finally merge until you have no reversing field left anymore. A little bit different to the previous picture, where it was the current sheet which was growing and growing and growing, filling more and more hot plasma, which was causing the total magnetic energy to go away. Finally, when you've got rid of all the energy, everything gets constant again, all the energy in the waves, that is. If you now start off with a net magnetic field phase averaged, then you find that the waves go away more quickly, because the sheets approach and meet sooner, and therefore you have some field left over, but nevertheless no waves to dissipate, and therefore you carry on at constant gamma and constant sigma. That's where the termination shock of the Crab is. So you may think this is all a little bit academic, and you may be right, actually, but this process is not complete by the time the plasma has reached the termination shock. In fact, since sigma is of order 10, still 90% of the energy is locked in the waves and the magnetic field at that point. And this is why it didn't receive very much attention, because if you just want to model the nebula and you're assuming some input, then this kind of thing doesn't change the interior boundary conditions on your flow. It's only a 10% effect on that. Well, what do we know about the stability of these stripes? Now we have, of course, lots of groups doing large-scale simulations, and one of the simulations they do is to see if the stripes are stable. So this is a paper by Jonathan Zrake from a couple of years ago, in which he tried to repeat Coroniti's estimates. Here is the striped wind with a slightly nicer picture of the current sheet. And he made a PIC simulation of a section of the wind. But he was forced to do this in a co-moving frame, and found indeed that the stripes go away rather quickly. So this is a time sequence. The contrast is, if you like, oppositely directed magnetic field. You can see that the whole thing becomes very scrambled and ultimately turbulent. So his point here was to say, this is how quickly they go away, and he agrees with Coroniti that, in fact, probably there shouldn't be anything left except turbulent plasma when you get out here to the termination shock. But unfortunately, the effect which stops this was not included in the simulations, because you cannot, or at least nobody has so far been able to put the idea of bulk acceleration of this box into the PIC code. So you cannot incorporate this time dilation and acceleration, which should necessarily accompany the dissipation, into the code, and therefore it's still not clear, from my point of view, whether this happens, whether the stripes do go away. Perhaps in very high density cases where the acceleration is not so strong, it's possible that they decay beforehand. But are they launched? Well, we now have global simulations, which extend out to several hundred light cylinder radii, starting off at the surface of the star, although the star in this case has something like 1/3 of a light cylinder radius, which is rather expanded, but it's perhaps just a detail. And indeed, these guys, Benoit Cerruti and Sasha Filipov, showed that you do launch something which looks like a striped wind. So here we have the rotating star, and they have chosen for an interior boundary condition the so-called split monopole. So it's a uniform field going out on one side of the surface of the star and in on the other side. Okay, that means you have a very, very singular structure of the magnetic field at the surface, but nevertheless, see what it gives you. Density and magnetic field. At least out to a couple of radii, we seem to have these current sheets very sharply defined and built up. The density here, you can see, is quite large in that part of the magnetic field which closes. Some parts of the rotating star capture the plasma and don't let it flow out. And in this particular simulation, the program feeds more and more particles into that region, so it gets to be a very high density, even though there is, the particles have difficulty escaping. Well, these guys also suggested that from their simulations, the stripes will go away, in this case at about 100 radii. You can see now, remember this is a PIC simulation, so they already have difficulty with accommodating the microphysical scales and the macrophysical scales, but they're now going out to 100 radii, which is quite an achievement. But the stripes do seem to get very, very much weaker when they get out. What can one say about this in relation to the Crab Nebula, for example? Well, the strength parameter of this wave is 10. After all, it has to be simulated, whereas the strength parameter in the Crab Nebula is 10 to the 11. A little bit of an extrapolation. Furthermore, and perhaps more important even, the initial conditions, which I mentioned, the build-up of plasma in this trapped part, mean that the current sheet gets lots and lots of particles, more than you might expect it to get in a real pulsar, and therefore perhaps goes away more quickly. Fortunately, we're not restricted to theoretical investigations, but there is an observation, and that is of the double pulsar system. Many of you may not know this system, but it became very famous. It consists of two radio pulsars orbiting around each other, with their orbit almost perpendicular to the plane of the sky. So basically, they're doing this. That means that there are also eclipses, and imaginatively, one of them is called Pulsar A and the other Pulsar B. One of them is fast and the other is slow. One of them is powerful, the other is weak. But you can read in this paper here that the 44 Hertz magnetic dipole radiation, that's the stripes, of Pulsar A are actually changing the pulses from Pulsar B. Now, Pulsar B is nearly 2,000 light cylinder radii away, and so the stripes, it would seem, must survive until at least there. Well, it would be nice to repeat this and to get a much more detailed analysis of the pulses of these objects, but unfortunately, they have to wait a little while for that. These two pulsars are also precessing. The spin of one of them has precessed so much that the radio pulses now no longer hit the Earth. And so there is now only one pulsar in this double pulsar system. And the encouraging news for the younger members of the audience is that you can estimate how long it takes before it precesses back. And one can see two pulsars again. That's going to be 2035. So maybe not. Okay, so let me summarize this part of the talk. Pulsars, it seems, don't launch an electromagnetic wave, as Pacini was suggesting, but more an MHD type wave, stripes and magnetic field. Theoretically, you would expect slow wave damping, so these stripes should still be there at the termination shock. Simulations don't back that up. And observations are also suggesting that maybe the stripes do find a way of surviving. So that was the stripe wind. I think, in the interest of time, I'll skip straight to gamma ray flares, and if anybody wants to know about that, maybe we can talk afterwards. So if you close your eyes for a second or two whilst I zip through these slides. It's not going so fast. It did go fast. Yes. Gamma ray flares. I promised at the beginning to come back to this picture of the synchrotron spectrum of the Crab Nebula. And now you should look not only at the black points, which are the steady spectrum of the Crab, but also, first of all, at these grey points, which are the pulsed emission from the central object, from the pulsar itself. So there's strong radio emission, and there's optical, and also X-ray and gamma ray. But especially, you should look at this blue point here. In April 2011, within the space of a few hours, 10 hours I think was the fastest time, this object was observed to increase its luminosity by a couple of orders of magnitude in the gamma ray regime. Now, gamma rays around here are very, very much weaker both than the pulsar and than the nebula itself. So this is nu F nu plotted, and this is where all the energy is basically coming out. However, during these 10-hour or one-day-long flares, something like 10% of the entire luminosity is appearing in gamma rays. So this is for theorists a major puzzle. First of all, it can only really be synchrotron emission to get this timescale at all correct. The cooling time has to be short. But synchrotron emission at 400 MeV is a major problem for all acceleration models in astrophysics, and that's because astrophysical acceleration requires gyrations within the accelerating object. It has crossings of shock, or it has drifts along an electric field or something like that. And you can easily show that the time in which one of these particles will lose its energy, independent of the magnetic field strength, is very short compared to the gyration time. So it can't be a standard type of acceleration model. Variability on the timescale of hours means it must be a really small source, and the fact that it's got 10% of the entire nebula, which is light months across, is also a bit of a problem. Is it reconnection, Doppler boosting, magnetoluminescence? You can find something like a couple of hundred papers on these suggestions which have appeared in the literature. My main problem with them is that they don't seem to be very predictive. They say, oh, well, it's possible to get very fast flares with a lot of energy if it happens to be pointing at us, but there's no real firm prediction made by them. So with Guenel-Jacinthi, we tried to look for a model which might do a little bit better, and we came back to the inductive acceleration of the wind, which I talked about in the first part. So the idea here will be to go back to this picture where we have an MHD type wind, and at some point the inertia becomes important and causes acceleration, but it doesn't actually get all the way to dissipating the waves until you get close to the, until you would actually have to go beyond the termination shock. So this is what it looks like with normal Crab parameters, and that is a multiplicity of 10 to the 4. That means lots of pairs going into this wind, and if you distributed them, the energy equally amongst these pairs, you get a Lorentz factor of about 10 to the 6. But we know that the radio pulses, which are presumably made near the surface of the star where these particles are being created, are a little bit intermittent. At least the giant pulses are very intermittent. So what would happen if we tried to turn off the fuel supply, the supply of charge carriers? Now, you can estimate how low it could go, and it could go to somewhere like a multiplicity of 1, which would mean that this mu parameter becomes very large, about 10 to the 11, and if I now put that on here, the MHD portion of the wind stops much earlier, and the acceleration proceeds linearly. Again, only 10% of the energy in the stripes is dissipated before you reach the termination shock, but by that time the particles have an energy of several PeV. So this looked promising because if you were to turn off the supply of pairs, it would mean that you inject into the nebula now, suddenly, because you can turn off this supply very rapidly, the millisecond timescales are present at the surface of the star, you inject PeV electron-positron beams into the nebula. It's an interesting little exercise to compute the radiation you would expect from such a beam radially collimated entering the nebula. And the kind of picture you draw would be like this, that in some section of the wind, which is includes the Earth in its solid angle, you have pockets in which there is very little plasma. In these pockets, which incidentally retain their identity all the way out, they don't dissipate on the way out, that's a relativistic effect. In these pockets, the particles would have extremely high energy. When they get into the nebula, they first start to be deflected slowly by the magnetic field and cool at the same time. And again, independent of the field strength, you can estimate how quickly they're deflected, through what angle. It just depends on at what energy they're radiating the synchrotron radiation. If you put these things together, you can estimate not just the spectrum, but also the time scale on which the emission should rise. If you're looking at Earth, initially you see only high energy particles, but as the cone broadens, the spot you would be able to see on the termination shock would grow. Of course, you can't resolve it with instruments at the moment, but nevertheless. And you would start to pick up lower energy photons. With these estimates, you can put some points on a plot here of frequency of the maximum synchrotron energy in GeV against the expected synchrotron flux, nu F nu again. And all of these dots are known pulsars. I'm assuming that they don't have termination shocks, which means that this process can go to completion and then inject somewhere even further out. Unfortunately, the measured positions of the termination shock limit this process, so that all of these pulsars fall off to the left, except these three here. So now this is the expected synchrotron flux, which arises when the termination shock stops the acceleration process prematurely. It also reduces the intensity a little bit, as you can see. If I put these then on another plot, and now with the actual spectrum, not just a plot on nu F nu, then you would expect this kind of spectrum until that solid angle I showed you, the particles were deflected through an angle bigger than that cone, in which case then you would expect the spectrum to turn over. So this is the Crab. Of course, it's very powerful and not too far away, so you might get flares like that if there's an interruption of the pair supply. And here are two more pulsars. These both, unfortunately, in the LMC, and so the expected gamma ray flux is rather lower. You can see this one also is not very convincing because it would only have a nu max of, well, less than a GeV, whereas we have about 4 or 5 GeV for the possible radiation from this pulsar. If I now put the spectrum of that 2011 flare from the Crab on here, you can see, at least if you made this model yourself, you will be convinced this is an excellent fit. It just means that you have to reduce this by a filling factor of about 10. So in other words, that cone of emission during this flare was on average 10% empty. The pockets of empty plasma made up about 10% of the volume of the flare. Well, you can be optimistic and look and see if there are other objects too. Here is 3C58. I've kept it on this. It's another powerful pulsar wind nebula. But I have to get it to this point, assume that the termination shock is much further away than it is measured to be. Of course, you can only measure its position projected onto the sky, so you don't actually measure the distance of the termination shock along the radius vector to you, so it could be a little bit bigger, but I think this is still rather unrealistic. Here is another pulsar, it's this one, which is in a binary system, And so, we don't, it's a millisecond pulsar too, and we don't actually know where the termination shock is. Towards the binary companion, it's presumably quite close to the neutron star, but away from the binary companion, it could be a long way away. Still, it's a marginal object because with only 100 MeV as the maximum frequency, it wouldn't really stand out so much. But this one is a promising case, and indeed there are some Fermi conference papers which have claimed to see flares from this object, which would be in line with this prediction. Okay, well, to summarize my take on the gamma ray flares, I think that the inductively accelerated wind also succeeds in explaining the three main puzzles of power, variability, and having synchrotron radiation at such high energy. But it also makes some predictions, I think, which is a strength. If we get to better observations of these flares, we may even learn how often the pulsar current supply has to turn off to make them, and how quickly it turns off. Gives us insight into the creation process. All the particles doing this radiation, I should comment, are created out of the vacuum in the magnetosphere. And it's thought that this happens by a process called magnetic pair production, which is, if you look at it from the physics point of view, a non-perturbative QED process, now like tunneling. This process has never been observed in the lab, and who knows? It's a fundamental problem which we may not understand fully, and which we may have access to in the next few years with lasers. But that's another talk. This kind of model can also tell you something about the turbulent fields in the nebula, because when you inject very high energy collimated particles into a turbulent magnetic field, you get all kinds of features which tell you about the waves in the turbulence too. So these will be more in line with the giant radio bursts, for example, or something like that. And there may be other objects which have these flares. Okay, so with the exception of the termination shock, I have reached the end in time, I think, so I'll stop here and try and answer any questions you have. Thanks.
So, thank you, John, for this excellent overview of the wind acceleration mechanisms in pulsars. There are many questions. Let us start with the first one.
Thanks for the interesting talk. I have a question concerning initial ejection and initial acceleration of particles. As you mentioned, one can't accelerate protons because one has to spend a lot of energy. One can work with positrons or electrons, but at least have initial acceleration. I remember from course of physics, one has to have electric field.
Yeah.
And the question is, where is near pulsar one can get electric field that allows to accelerate particles?
Yeah. Okay, so
Current opinion.
Yeah. So if you ask what are the electromagnetic fields surrounding a perfectly conducting, rotating star with a magnetic field embedded, then you find that there are electric and magnetic fields. Of course, in the wave region, they're perpendicular to each other, so that doesn't help. But near the surface of the star themselves, there's a component of the electric field along B. And it's basically this electric field, which comes from the rotation, which is able to draw particles, electrons, positrons out. And as soon as you manage to draw one out, if it gets accelerated to high enough energy, it starts to emit high energy photons in the curved field, and these then make pairs by the process I was saying is not yet observed in the lab. So it's a pair cascade which starts because of the rotational electric field, and actually presumably happens within a few stellar radii for these objects.
Sasha Huni has the next question.
You started your presentation by saying that there are 50 known nebula and about 3,000 known pulsars. But if I look at your striped wind model, I don't really understand why not many other pulsars also have a wind and should have a nebula. I mean, it seems to be a mechanism that should basically produce nebula around most pulsars if the magnetic field is strong enough. So
okay. So I think the key is just in the power which is available and whether this can produce something with a surface brightness that is visible. The few examples which I've been talking about here are the 3 or 4 most powerful pulsars, and you can and the young ones too. So it's that kind of selection effect. I would certainly expect a striped wind from all pulsars, but the amount of energy which it would have would be rather too low, I think.
And I had another question, if I may. For the gamma ray flares, do we understand why they happen sometimes and many times not? I mean,
well, no, is the short answer. Of course, the models which are being produced, magnetoluminescence, etc., all start off with some kind of situation which is inherently unstable and show that it goes away quickly. But it doesn't tell you how often you get to these initial conditions. And the theory I've been presenting here also bypasses this problem by saying, if you turn on and off the supply somehow, so that is pushing the real trigger question down to the level of how do these cascades work when the particles get drawn out of the surface? Are they bursty? Do they always go in the same direction? Do they drift around on the surface? That kind of question. And we cannot answer those at the moment. There are some now ab initio simulations of the inner magnetosphere, but they all take pair creation processes which are ad hoc. Nobody is actually looking at the real pair creation by the curvature photons from the,
Thank you.
Next question here.
I have a couple of related questions. So the PIC simulations showed that the magnetic field was fully turbulent at the point you reached a termination shock. Is this always the case, independent of the distance to the termination shock? How would this change if bulk acceleration is included? And how does the magnetic field, sort of just before the termination shock, relate to that in the nebula?
Okay. Basically, this is the content of this part of the talk. The idea is that the PIC simulations cannot include, at the moment, this bulk acceleration process. And so the conclusion you can draw from those is not firm, in my view. I personally like to imagine that the stripes continue out to the termination shock. But they must disappear there, because outside in the nebula there's just too much plasma to enable waves of this frequency to propagate. So the question is it really an MHD shock, or what happens at the termination shock? And in fact, I was going to present 2 pictures. One of them says that there are waves reflected from the inside of this boundary, and it's the thermalization of those waves with the outward propagating particles which gets rid of the stripes within a thin layer, which is actually, you could call the termination shock. So in that sense, the pre-shock field would be oscillating and perhaps contain a phase average component. The post-shock field would have no more oscillations, but would still contain a phase averaged part, which had been compressed in the usual MHD way. And so I have a whole theory and a recently submitted archive paper which tries to explain the X-ray spectrum on the first of those 2 pictures. The global simulations which include the equatorial current sheet, which is there in addition to these stripes.
I have maybe a naive question following up what Sasha has been asking. So ultimately, the energy comes from the rotation of the pulsar, and it is mediated by the strength of the magnetic field that it has. So is there then a correlation of, the size or the strength or the emission from the nebula with the rotational period or what we know about the magnetic field strength or something like that? Or is this a way to address his question that only 50 out of 3,000
right.
have these
50 out of 3,000 is not very many. If you want to have the position of the termination shock measured, that's even fewer. I don't know offhand how many there are, perhaps only half a dozen. A little bit more maybe. So I think there's observationally no clear relationship seen between the standoff distance and the spin down power. Okay. But yes, you're correct. There must be one there. It depends on the ambient pressure and, of course, on the power you're emitting, how big this bubble grows, how fast it grows. Yeah. In the case of the Crab, everything fits in nicely. The estimated magnetic field is, in fact, close to the 1 milligauss in the nebula, which is derived from observation.
Yes, Christian Fendt. Here's the mic.
I have a question about the peak simulations and the stripes. So what is the size of the stripes? What is the length, in radial direction, and how well do the peak simulations match? Do they cover a number of stripes? And so peak simulations do not treat single particles, the
no.
Big particles. How many, let's say, electrons are in one peak particle in the simulations, and how realistic are the simulations then?
Oh, I think they're totally unrealistic, but that's because I didn't do any of them. It's a gigantic task because the strength parameter means that your gyro radius is very small compared to the wavelength of the wave. And the wave itself is 10 to the 9 times smaller than the termination shock. So where did I show this? Yeah, here is a co-moving one. There it doesn't really matter. He can choose his box to just have 10 wavelengths in it and see how fast they go away. That's okay. But if you want to do a global simulation down here, Benoit Ceruti is the one I showed you is I think at 150 radii, which is only a factor of 10 to the 7 short of the termination shock. So it's a huge problem. But we have to really understand whether these waves are launched and if so, how, whether they're really sharp discontinuities or smooth out. And that you can only really do by PIC, because the kind of analytic solutions I was showing you are very simplified, and it's not clear that nature actually goes close to one of them.
I see no more questions. Before we thank John, let me announce next week's speaker, Lisa Cooley from the Australia National University in Canberra, will talk about galaxy formation and evolution in 3D. And do you have time for drinks and dinner later on? So if you're interested in joining us, please come down here and then we go over to the Neunheim Marktplatz. It's not raining, so we will meet there. Okay, with that, let us thank John for this very nice talking lecture.